Anyway.
My name is Brendan, and this is Subsystems, basically 101 and 1678's a pun from our old mentor, and we couldn't take it off because we miss him so much, because he's in Boston. Anyway.
Yeah, and I'm Jen. I'm one of the mentors for Citrus.
Yeah. So just starting off with who I am and why I'm talking about this, my name is Brendan Rockwell. This is my 4th year in FRC. I'm currently the design lead on Team 1678. This is kind of just an idea of like what I got out of Citrus and robotics was basically just how to work in a professional environment and work on the iteration process for design. So that's what we're going to talk about today.
And I'm Jen. Like I said, I'm one of the hardware design, and I also do a lot of outreach mentoring for 1678. In the daytime, I work as a mechanical engineer at Terra-based Energy. It's a solar startup. And this is my 5th year in FRC.
Yeah, so just kind of starting off with what this is actually going to be about. We're basically going to start off with how do you iterate using a case study from the 2022 robot, so the Rapid React game. We're going to talk about the tips and tricks that we use to speed up our own development, and we're also going to talk about personal little bits that the only time we shared before was in this presentation last year. So the case study that we're going to be doing is focusing on the hopper. So coming into last year, I don't know how many people remember the game, but you had 2 colored balls, one for your team, one for the other. It did 2 things on our team. We had ball storage and we had ball sorting. So if the ball came in through here, we would intake the ball, and then it would either go out from the back if it was the other alliance's ball, and if it was our ball, we would queue it up to be shot. So we wanted a couple things out of it. We mainly wanted it to be automated, simple, and reliable. So with those kind of ideas in mind, how did we actually get to that point on our robot that we ended up bringing to competitions? So where did we start? At the very beginning of the season, we kind of start with the what's and how's of our entire robot. But not only that, we kind of start off with the what's and how's for each individual mechanism. So we're talking about what do we want each mechanism to do, and how do we want it to do it. So if you see over there, I see that it's supposed to hold 2 balls, and we also weren't sure, but we thought maybe having balls while climbing would be important, maybe trying to like take another alliance's ball while we climb to slow them down from scoring, or something similar. So we kind of had those 2 ideas coming into the season.
Yeah, so jumping off that, basically this list, this whiteboard you see in front of us, is a culmination of like a day's worth of conversation with our entire team. The students all break up into subgroups, kind of just spread out another where they do design, like business and media, fab, whatever it is, like they kind of just break up, and they start by taking a rules test to learning exactly what you need your robot to do. You can't design a robot if you don't know its limitations. For example, in this year's, the 2022 game, you could only hold 2 balls, so there's no point in designing a hopper that can hold 3, because you're gonna, it's just extra work that you don't need to do. So all the kids take a rules test, and then from that rules test, they start with everything that a robot could do at the competition. Notice that over in our drive section, like, they might be really, seem really simple, like, oh, we want to drive fast. But if you think about, like, the game where you were shooting up into a hoop and the balls came out randomly throughout the field, so being able to, like, go to the other side of the field really quick to get your ball is kind of crucial, right? If you're spending half your time just going after the ball, you're not spending that time shooting. So we just make a list of absolutely everything a robot could do, and then from there, we narrowed it down to what we want our robot to do specifically. So that's what this list here is, specifically what our goal is for our robot of that year.
So kind of where we'd like to start each year is looking back on previous years and trying to find similarities, trying to find differences, and figuring out what we can take from previous years to at least get an alpha bot done, and hopefully being able to apply those lessons to our comp bot as well. So we kind of thought about what are simple robots that do something similar to the 2022 game, so we can try to figure out the most optimal way to do something. So for last year's game, we were thinking about 973 from 2021, where they had a really simple robot that was still really effective, because it would basically drive around, pick up balls as quickly as possible, shoot and score them, and it was a really great idea. So we kind of want to take ideas as much as we can, so you're not having to spend as much time innovating. We basically are trying to build the lowest effort first prototype, because when we're starting out in the season, we don't know how game pieces are going to interact. We don't really know how things are going to go, and so we need to have a core idea of how things go before we can actually start building a comp bot. So going back to what Jen was talking about, the what's in-house discussion, we also then spend some time drawing up how we think that can work. So it's just everyone gets a piece of graph paper, everyone gets a pencil, and you kind of jot down what you think can happen. And then we also have little mock-ups of what the ball looks like, because a lot of the times you think you can do things a certain way, and you realize, for example, 22 had a really big game piece. So if you think you can have like 2 sitting right there, right in your drivetrain, well, you don't really have that much space in those drivetrains. So having that really helps out. So it's me right there, having like a 973 similar style with an adjustable hood. We had our design lead at the time over there drawing a pretty similar robot, and then just to give you an idea of how it works, we set up a scale using the ruler. Everyone gets graph paper, everyone knows what the scale is, and from there we kind of start designing how we think a robot should go.
Yeah, and like we said, everyone on the team is doing this too. We take our ideas from the whole team, not just like the designers, so that everyone has their input into what the robot should look like. Okay, so from there, based off of, we kind of draw out some ideas, you look at your list and you think, okay, which one looks like the quickest one, the simplest one to do. You pick that one and you start prototyping. So like we said previously, we used 973's Hopper as our example for the 2022 robot. We had proof in that year of them doing quick cycles with it, being able to pick the balls efficiently. So we went with that as our one to start with. So really what you want to do within your very first week is you want to be as quick as possible as having like a janky kind of mock-up of what's happening. Like we said, you need to figure out exactly how the game pieces interact. In that year, they're like kind of bouncy balls. You want to like figure out how much you want to compress it and pick it up and stuff. So you just kind of build as many like plywood, very basic type like prototypes. And if you have more than one idea, that seems like a valid way to go. If you're like, I don't know between A and B which one's going to be better, then just do both, because these are really low effort, so you can quickly like process and pick out what works and what doesn't work.
Yeah, like Jen was talking about, these are really not polished prototypes. You don't really need any machine other than 2 sheets of plywood and a drill. And then if you want to have them connected, you can just cut pieces of 2x4 and use wood screws. These are like, you're basically drilling a hole, putting a shaft on it, and then you can power with that same drill just to see how those game pieces are going to interact in these sub-assemblies. Because you don't really know like how a handoff is going to work or how a shooter is going to work until you actually put stuff together and see how it functions.
Yeah, so I think we have some examples of our, let's see if I can full screen it. So as you can see here, just pieces of plywood. At the ends of these shafts, they're just holding drills to it. So nothing fancy, they're just trying to figure out how quickly, like how can we shoot this ball up once we intake it. All right.
And then once you have like an idea, like that one was working okay, but we noticed it was like getting kind of close to a dead spot in the middle just because they were far enough apart. So then we made a new one, basically just by drilling new holes into pieces of plywood and seeing how that worked. So this is a new and improved one where it's basically the same thing. You just make slight adjustments to it to see how it works. But you notice how we had another problem, and then after that we just built another one. Because with plywood, you really can just keep cutting stuff and keep seeing how it works. And then the other really important thing you're doing here is take measurements. Because your goal is to find out how things work. So you basically want to rip quick prototypes, take the dimensions of stuff, see what works, see what doesn't, and take that information moving into the next one.
How do I re-enter full screen? Sorry. What do I press for? Sorry, okay. Slideshow, there we go. All right, cool. All right, there we go. Sorry about that. All right, yeah, so like we were saying, you want to find what doesn't work with your design. So like in the previous video, it was getting caught up at the bottom. The pulleys weren't really pulling up that ball. If you notice that, you don't want to be, well, that's just an anomaly, right? Basically, you want to be doing this enough times that you can see that it's like constantly doing it, so that you can learn from the mistakes. Because if it happens once in your prototype, odds are if you continue through with that design, it'll happen again when you have a full-fledged robot. So you want to see where things are not working, where things are getting caught up, so that you can fix that and get rid of that bug within your design.
Yeah, and then also these are just kind of the general things you want to be taking into your actual design. So the real goal of prototyping that we like to have is we want to figure out the center to center, so basically how much compression we want to be putting on these balls. We're trying to find the speed of how these balls like to move. So if it's an intake, we know that it wants to spin fast, but the question is how fast? Because that's going to influence your motor ratios, it's going to influence your motor usage for software. And you basically want to be figuring all of that out as early as possible, so when you're making these quick prototypes, you know what you're working. And then an example of what happened here when we found out something didn't work was we realized that in order for this to function as something that brings up, you would want a feeder wheel because otherwise there's nothing actually driving it up enough because the two little loops of polycord was not cutting it.
Yeah. So at this point, I believe these are like two different prototype groups. So like someone was working on the shooter and someone was working on the hopper, and we just put them on top of each other to see how it would work together.
But the really important thing here is to not just assume that your prototype is perfect. So it can often be challenging to figure out that your prototype maybe isn't working. It sucks a lot of the time. You're like, but I put so much work into this and now it doesn't work well. It sucks, but it's an unfortunate truth you really have to come to terms with. Because if you start off with something and you're trying to tell yourself that it's working well and you build a whole robot out of it, that robot isn't going to work well. But if you start off and you realize that your idea isn't working well, like this idea wasn't, we realized, okay, this is going to work for a practice robot. We still need to prototype more. We still need to work harder on finding a different solution because right now this one isn't going to work. So it's okay to fail. It's probably like the big takeaway of this presentation. We're going to talk about it a lot. It is okay to fail. We do it often. We have a motto of fail faster. We want to be, it's okay to fail, but we want to do it quickly so we can move on and try to make improvements. An often thing that you can do is obviously you can't try to perfect everything because perfection isn't really going to exist in these games, but it's really easy to make like just a T-chart of what is good, what is bad, and fill it out. So then we started talking about what can we get out of this mechanism, right? So we had this, but it wasn't really dealing with what we wanted of like, the balls were going to have to get sorted by the shooter, but then that would be complicated because then we couldn't just be shooting as much as we wanted. So we kind of realized that sorting was a really important thing, and then we were starting to think more about how can we get this to be giving us the other stuff that we want.
Yeah, so also it's important to keep in mind here that we didn't build these structures, run the ball through once and say, okay, it works, move on. Like, the kids were constantly putting the balls through because if you think of, like data points for whether it's good or bad, if you only run it once, you only have one data point. So you want to run it like 10, 50 times because when you're playing the game, you don't pick up a ball just once, right? You pick it up X amount of times throughout the match, throughout the whole regional. So you want to know how many times out of 10 or whatever it's working for you to really decide whether it's a good or bad design. Had another point that I was going to bring up, but
one other thing that's really cool about prototypes is also like if you're building something like an alpha robot or something like that, it's okay to give yourself leeway in how it works. This isn't as common on this one because we didn't really have time to think about that, but for the shooter, we basically have these web of holes, so we don't really know how compression is going to go on the shooter. So for that to be real, we had a bunch of different holes, so we could basically move the backing around and find out what compression was going to work better. So give yourself leeway when you're still, even if you're making a prototype robot, still give yourself the opportunity to experiment, find out what works, find out what doesn't, and most importantly, run a lot of tests. So after that, we kind of realized, well, if we're trying to do sorting, we need some way to actually sort it, and that's where this came in. We found this idea, well, actually a mentor at the, found it and sent it to us, and he was like, this is a really cool idea because they're basically doing what we want in this. So this is a Vex bot that is basically doing exactly what we want. And we saw that and we thought, that is a really incredible idea because they're trying to pick up red, they pick up red, but they can also just pick up blue, not worry about it because it just comes out. So when we saw that, we realized that is something that we really want to have on our robot because it obviously is working really well, and that's a really cool idea that we wanted to implement. And so a really important thing to think about for all of this is don't just get in your own head about, I need to come up with every single thing. There are lots of smart people in the world. I recommend stealing from them. We do it almost every year where we like to say steal from the best and invent the rest. So if you find a really good idea, try to take it, try to improve it a little bit where you can, and it's really important to take ideas from everywhere that you can, not just like your own brain.
Yeah, and it's important to note that this decision that we needed to be able to sort the balls quickly came from thinking about how the flow of the game is going to work, right? It's easy to get really like tunnel visioned on, I want my robot to be able to do this, but you really need to think broadly. So like, for example, for this 2022 robot, as you know, there's red and blue balls on the field, and they're just coming out randomly from the shooter at the top, right? So if you want to be quick in picking up the ball, you have to have a way to distribute get rid of a ball that you've picked up that's the wrong color, right? Because if you drive into a grouping of red and blue balls, you want to be able to ensure that you come out with the two colors that you want. So thinking through the process of this, and trying to be efficient in mind, it's okay, we take in two balls, how are we going to spit it, get rid of it? We're going to spit it out of the top, or we're going to have to drive it out backwards. What if it's the first one we intake? Exactly those kind of mechanics of how the game is going to work overall really drove this decision to look deeper into what we can do with the sorting, because you want to kind of simulate gameplay in your prototyping as much as possible. There's a really funny video from this year's 2023 of one of our students sitting on a rolly cart, holding our intake, and had two drills, and a student sitting pushed him with the rolly cart into the cone to see how to pick it up. So really simulating the gameplay of okay, what's going to happen when we drive up to the game piece, all that kind of stuff. Yeah, it's things you should be thinking about when you're prototyping, not just your thing, but how the game's going to work overall.
Yeah, and then one more thing is that when we're talking about getting all these quick prototypes out, there is another major benefit that is, even if your prototype or that you put out isn't perfect like ours wasn't, it's okay because you're still getting driver practice in. So obviously a really big part of FRC is making sure your drivers have practice, making sure they get how the game works, making sure they have a lot of experience. And on the design side, that also helps you a lot because you get to observe it in match situations. So even if you can't get a full drive base out, using a kitbot chassis is still really great because it lets you move something around, see how it's going to interact, and that's also how we found out more about the gameplay, like Jen was talking about, is we were watching our driver run around and he would have problems where he's shooting the wrong colored ball all the time because he couldn't differentiate without doing it manually or with the shooter, and so he was accidentally shooting the wrong ball all the time. There we go.
All right, so once you have all this data that you've collected from your prototyping, what do? Well, you do it better, right? So you take a step back and you really look at your list of what's that you've made at the beginning of the year. We took a picture of our what's. Those are our end goals of what our robot needs to be able to do. And we realized that our robot was not fully reached its limit because it wasn't able to, go in and quickly pick up two balls. It was going to kind of a chase thing. Like we said, he was shooting the wrong kind of balls. So we got this idea of the being able to shoot it out. So we had this idea of doing a flap, right, to kind of switch directions and whether the ball goes up or gets shot out. And so this doesn't need to be a full-scale robot at this point. I think it was still just prototyping bits, but basically you just shoot, I lost my train of thought.
Basically, you're just trying to, again, take those pieces of plywood, you're cutting them to a reasonable shape, and then you're just putting in these shafts, and you're seeing, okay, does this idea work? So here was the flap that we were making, and then basically, I don't know if you guys can see it, but we were just sending a ball through, and if we wanted, we would flip it up, and the ball goes through the back, and then if we wanted it, we would basically keep the flap down, and the ball goes all the way up. But the really important thing here is, again, you're not trying to make a perfect robot. You're not even trying to make a full robot with a lot of these prototypes. You're just trying to make a concept that will say, does this work or does this not work? And if it doesn't work, we need to think more, and if it looks like it will work, then we've got to send it. But the really important thing is that it has to be good enough for you to run a lot of reps with everything. So, like we like to say, hours, not minutes. So you can't say, oh no, I tested it for 5 minutes, the ball ran 20 tests and it worked great. Because the 20 tests might work well, but then when you start changing speeds, it might stop working as well. When you start changing other things, it's not going to work as well. And you really have to make sure you're getting as much practice with each thing as you can. Otherwise, you're not going to know, you're not going to really have a good understanding of whether what you're doing is going to work well or not in actual match play.
Yeah, your end goal is to be reliable as possible. And so the amount of times you repeat the process and prove that it works, the less likely or the less risk you have of it breaking because you've run it for the same amount of, closer to similar hours that you run it within a regional competition.
Mm-hmm. So after we did that, we did the same thing again. We took that concept and we built a better one. So this was kind of a thing that we were doing for our beta robot. At the time, we thought that was going to be the design that we were going to take to competitions. And so we basically had this whole thing built out. We had like a feeder wheel leading into the shooter. Then you had this whole system where the ball comes in through here, gets spat out the back, and this hatch is going to do all the work for us. So we were building a much more high fidelity, high quality prototype where you're basically saying using metal, you're using actual things that you would put on the real robot. And so you're just improving everything, you're building a better one over and over, and then you're still running a lot of tests with this. So now that this has motors on it, we're still going to test the heck out of it. We're going to make sure that everything that is running through it is running well.
Yeah, because at this point, we had tested the flap method enough times that we're like, okay, this is a pretty solid idea. Let's build like you said, a metal version of it. Let's put motors on it and really test it out. And so that's when we discovered just kidding. Yeah. So yes, we'll get to what we discovered in a second. But yeah, so at this point, we're dropping it onto an actual robot, like drivetrain, so that we can drive it around, test it out, have the driver test out how it works, like we said, going up to the game pieces instead of someone hand-feeding it, just to see really if this idea was going to work.
And this is, again, another example of the hours, not minutes. So we had our driver, he was going around and he was just testing again and again and again. Does what we think happen, and does everything work smoothly? Is the handoff from the intake to the shooter good? Is the handoff from the indexer to the back good? Is the handoff from the shooter to the indexer working? Is every single thing that we need to move well on this robot moving well? And if it isn't, then that's a pretty big problem.
And it's very important to be documenting these phases, like recording the driving, taking pictures and videos and stuff like that, so you can look back and see what exactly is happening. Because if it happens in the second, it's kind of hard to know exactly what was going wrong. But if you're videotaping it, you can go back and review that footage and say, oh, this is where it's getting caught up or something like that.
So then, again, practice. So you want hours, not minutes. You're trying to get as close to a real match situation as you can. So maybe you don't have the capacity to build a full robot. That's fine. But if you have a push cart, or you have anything that you can mount an intake to and run it into stuff, or for the indexer, if you have a way to throw balls into it and see how it comes out. So you're just trying to make sure that you are getting as close to a real match as you can. And the really important thing is you want to try to limit test everything. So you want to know, if I send something through really fast, does it work? If I send something through really slow, does it work? If I send something through at a weird spin, does it work? You're basically trying to find every single possible thing that you can do to this mechanism to break it, to make it not work, to get something stuck. Anything that you can do to try to mess it up, do it. So you know if that happens in a match, are we okay or are we screwed?
Yeah, exactly. Like we said, our team's motto is fail faster. So you want to keep doing cycles until you figure out how the design is flawed. Because once you know how it's flawed, you can improve it, you can work around it, whatever it takes. Come on, buddy. There we go.
But then we did all that practice, and we kind of started to realize this isn't working right. So the really important thing is when you're doing all of this iteration, you really have to be honest with yourself of, is what we are doing working well? Is it not working? So you can do the T-chart, or you can say, hey, is what we are trying to accomplish getting done, or is it not? So if you're lying to yourself and you're saying the way you're doing is working when it's not, you're really just hurting yourself in the long run. It sucks to throw away a lot of your work. We do it a lot, and it always kind of hurts inside every single time, and that's okay. It's all right to say, wow, I really wish I didn't have to throw all of this away, but I do. So if you have an issue, you kind of have to address it every single time. Every time you fail, you're learning. And this is an example of things going wrong. So this ball was supposed to be ejected, but as you can see, the ramp was unfortunately just not moving fast enough. So this was a pneumatically activated ramp, and we could not get it functioning at the time. So here the ramp tries to come up to let the ball through, and we just don't have the time to let that happen. And so we had to say, okay, this isn't really feasible for us to make work given hardware that we're using. So if we fundamentally can't make it work, you kind of have to scrap and start over again. So if there's a problem that's pretty fundamental, you have to either realize how you can fix it or try to figure out a new idea to deal with it instead of the one you're currently using.
And what week were we in at this point when we had?
Week 4?
Week 4 when we had this?
Week
so
4.
We were deep into the build season when we realized we had rebuilt this whole robot, this whole structure, and shoot, this flap system that we designed around is not working, right? So it's very hard to be all that time kind of thrown away, right? But it's not really thrown away because you've learned your lesson from it. if we hadn't reevaluated and tested, we may have not gotten to this point until we were at a competition with this robot and would have been like, oh, this is not working. So learning, it's learning. There's no bad learning. You're learning what doesn't work so that you can get to the point where you know what does work. So why is the delay? Why is it not? There we go.
So then you come back again and you kind of go back to square one. If your idea doesn't work, you have to do something else. So our flap didn't work. What else could we do? So we went back to our our drills, we went back to our plywood, and we started seeing what can we do to make function. So we went back to low effort prototypes, and we had basically 3 shafts, each one with a wheel on it, and we just tried to see, does this work? So it's basically, does each new idea that we have to deal with the problem function? So if you have your old robots around, that's another great way to test your ideas, because it's an existing drive base, or it's an existing something that you can be working with. And then after that, you basically find what thing you think will work next. So your current idea didn't work, that's okay, move on to the next idea. And once you do that, you want to build a better one, and more importantly, you want to get a lot of reps on whatever you're using. So we built that. It looked like it was going to work on the polycarb. We ran it for a couple hours, and it was running well, so we built a new one. This was basically 2 sheets of metal that we cut, and what's basically in there is just drills powering shafts. And so we had this whole system where basically, if it is the color we want, they could bring it up. If it was not, we would bring it down. And this was basically an idea to make sure that the ideas of the geometry that we had were correct. And so throughout this process, we were moving everything around, drilling new holes, testing new things, and again, taking down your dimensions. Because when you're prototyping these, you want to make sure that you are writing down what is working, but also what isn't.
Yeah, that's why it's good to use wood and stuff, because if where you put the shaft or whatever, it doesn't work, okay, just drill a new hole. Like it's very low effort to just change things around to find really that golden quantity.
Mm-hmm. Right. So after we did that, we decided the metal one worked a bunch. We ran it for a couple hours again. It looked like it was working. So then we built a better one. And from there, we created our competition robot. So we had the same design of the wheels spin it either up or they spin it out. And we were basically testing everything that we could to see whether it was going to work, whether it wasn't. And this ended up giving us enough time because what we were working with was not actually giving the time with the solenoids, but because this is all motors, we actually had the capability to do so. And then also you can see an important thing is the rest of the robot doesn't have to be perfect for you to test a mechanism. So the shooter there hadn't really been dialed in. We hadn't done a regression. We didn't know what our values were. But what mattered to us was, does the indexer work? And so you can also go through subsystem by subsystem and make sure that what you are prototyping at the time is functioning. So for this one, shooter needed help, but this indexer was working great. We were really happy with it. So we said, it's good enough. It is giving us what we want and how we want it. And it was being really reliable. So the important thing here was we reached what we needed to happen at the beginning of the season, and we hit the goal, so it was good enough.
Yeah, it achieved what was on our what board, right?
So just because it's good enough doesn't mean you necessarily have to stop. It just means you don't really want to be changing the entire thing again. So basically, you want to keep going through your cycle. You build your thing, you want to test it a bunch. This not only gives your indexers practice, but it's also giving your drivers a lot of practice, right? So if you've got a robot working, make sure your drivers are driving it for as much time as you can, because the more everything is getting run, the better the robot will get, because you have more time with the robot, you have more experience with how the robot behaves, and everything is working much better. But the one thing you have to remember is that you have to think about what you can do that will guarantee you the most success. So if it's good enough, it's probably good enough. So you don't really want to spend your entire build season taking time away from your drivers to make tiny, tiny improvements to a mechanism, when instead you can be getting your drivers hours and hours of practice. So to quote the great late Kobe Bryant, once you know what failure feels like, determination chases success. So you want to make sure that you understand what went badly, and you want to make it good, but then you have to think about how to make everything as good as possible. So no subsystem is existing in a vacuum. You have to be making sure that your entire product is getting as good as you can. So you want to think about, what can I do to make the team the best, or the performance the best, not just the subsystem the best.
Yeah, so like in engineering, there is no such thing as perfection. If your system is working 90% of the time, like the effort it's going to take to increase that to like 91, 92%, inching closer to that 100%, really is not going to impact you as much as just having it consistently hit that like 90% of the time. Like we said, consistency is key. If you're winning one match, that's great, but you have like 7, 8 at a regional. So you need to consistently be putting out balls and stuff like that so that you have a good overall like scoring chance when you're playing. So you just want to like be realistic with yourself, whether or not, okay, does this, I'm gonna keep repeating this, but like, does this achieve everything, the what's that we set out to do this season? Okay, it does, check. And like, could it be better? Could it work better? Yes, maybe, but if it's working at its baseline consistently, that's better than just trying to inch forward and it not working as well, because you keep changing things.
Yeah. An example of like us having another improvement we wanted to do was we were thinking about if we added a side wheel, could we try to make it so that it would spin weirdly, so it would be harder for other teams to pick up the ball after we ejected it. But we were looking at it and we realized in order for us to do that, we're gonna have to redesign a lot of the robot, we're gonna have to relook at how we're doing a lot of things, and that made us realize that's probably not worth our time, and instead it's better to try to fix other parts of the robot and trying to improve stuff like gyro practice and software performance.
Yeah, like one of the examples of something that we did keep improving after we had our whole structure, it was noticed that the sensor that was picking up the red and blue, sometimes it would false read a color. So we spent like time like adding more lights, designing in like tweaks so that the sensor could better detect and not shoot out the wrong color ball. So like that is something that's like, gonna improve your performance, right? Because you're gonna more consistently pick out the right color ball versus something like Brendan mentioned where it's just like a nice to have.
So that is our presentation on iteration subsystem development. Are there any questions that we can answer? Yes.
How do you decide what prototypes you're going to do? What do prototyping teams look like?
Yeah, absolutely. So basically, when we're doing prototyping, we take all of our hardware members. So we have 3 hardware subteams: design, fabrication, electrical. Everyone who's on a hardware subteam is divvied up into groups with a senior design member as the lead, and then people from the other subteams filling it out. And then from there, we basically spend about the first week building prototypes. The subsystems are assigned to people based off of what the design lead thinks, so that's me this year, but normally it's just like, you give people mechanisms and then they kind of iterate from there.
Yeah, we basically take the top ideas from those drawings, we look at what the top ideas are, and if there's like several that we're like, oh, these could possibly work, then we just divvy them out as prototypes for these subgroups to test out. Like this year, the 2023 game, no one really knew how to pick up a cone, so we had way more prototypes going on than like previous years where it's like, okay, we're picking up a ball, we just have to figure out how we're gonna take it up into the robot, right? So it kind of depends year to year just how much prototyping you need, but really you want to just use the best ideas that you can't decide what to go with unless you do a little bit more digging into it.
I found your whole you have the mechanisms separate from a hot software chassis. So you created the mechanism first and then you put it onto
Yes.
chassis. Do you have a standardized chassis that you use kind of thing? Where you can just
Not really. We generally try to use a 26 by 26 drive base, so that gives us a little consistency to work with. We find it small and it works really well with swerve. We have a standard alpha drive base that we use, so it's basically just a base swerve with one center tube. So for alpha, everything's designed for that, but following that, we don't really have any specifics. It varies from year to year, but the general rule is there will always be some kind of a cross tube, and that's where most of your superstructure is going to mount to. And then besides that, it varies from year to year.
What does the prototype look like from week to week?
So it kind of depends on how each mechanism is going. Obviously for this, we had a wood prototype in week 4, which wasn't exactly optimal, but it's true. Generally, we're hoping to have a alpha robot done after week 1. And then once you have that done, you're trying to improve that into your competition robot. Hopefully that will be constructed by about week 3. Obviously, there's going to be iterations happening. What you put on the robot first isn't necessarily what's going to go to a competition, but you're trying to get something for drivers to practice with that will be good as soon as possible. Yep.
You mentioned classic prototyping is 2x4s, plywood, drilling holes, drills. So outside of those that you mentioned, what are some other tools that you're using?
Really, we're just trying to use that. It's also really helpful to have a lot of standard wheels that you're using. Wheels in FRC can vary a lot, so if you can have one of each or 2 of each type, that can often be helpful, so you just see how it interacts with each game piece. Besides that, Honestly, you don't really need too much. It's a pretty simple process of just how does this spin on a thing. And even if you don't have all the wheels, you can find similar materials. So you find out what plastic a provider is using, and you can work from there.
Like when you showed you showed most of the examples from the 2022 game with
Yeah.
the intake. How did you go about like prototyping with the wood and the 2x4s and et cetera? How did you go about that with the arm? Like,
Oh, so for the arm, it's a lot harder to obviously prototype with. We have the advantage that we've worked with elevators before, so we kind of know how them worked. Elevators also, you don't have to prototype as much. They're a pretty tried and true concept in terms of how you do a pulley setup and that kind of thing. So we did a lot less iteration on the elevator as much as we iterated what the elevator would mount to and what would mount to the elevator.
Yeah,
But-
we did try a wood prototype of a climbing mechanism in the beta, and it immediately
Broke.
fell apart as soon as it like took the weight of the robot.
Yeah, for
Yeah, for
2022, we tried to do a
2022,
climber
yeah,
and
with, where it had to, go up the bars. There was like a complex geometry thing that
Yeah.
was attempted with plywood, and it did not work. The robot just fell. First I had the video. I don't know where the video exists,
Yeah.
but it literally just immediately fell.
For a lot of the structural stuff, if you have something like a pre-drilled steel or aluminum, it's often nicer because it's not going to break as much. But for your more superstructure or like load-bearing stuff, it's often nice to have stuff like a climber in a box where it's pre-built and you can just throw on, or have like something that you can basically know how it works. You can iterate on top of a pre-existing thing.
So you can sketch a lot early in CAD, figure out like the new geometries and areas. How do you balance like designing logs early in CAD that that influences further prototypes versus just like building something and trying it out?
So the general idea that we do is we try to figure out the superstructure using CAD drawings. So if, for instance, this year we kind of figured out we wanted the tilty arm and with the elevator early on, and then besides that, the intake was almost left entirely up to prototyping. So your general goal is to have anything that is much more subjective to the game be done by prototyping because it's going to vary a lot more, but an elevator is going to be an elevator. So, yeah.
Yeah, and within the first week of sketching and prototyping, you're hardly touching the CAD. It's not until you get those measurements of like how much you want to compress the ball, like how much spacing we need between these rollers and shafts that you really dive into the CAD, because then you can easily get lost in the CAD and forget to like test it out in real life. Anyone else? Yeah.
When you're putting your prototypes together, obviously it's like not the most integrated thing at that moment. And then when you release like when you do a metal version of bot, you're going to have better integration. Doesn't it change the way or do you guys have problems with that at any point? Or?
So the really key thing for subsystem handoffs is to do as much as you can with your movable prototypes then. So for instance, both the shooter and the indexer that year both were adjustable on that alpha robot. So we figured out the dimensions by basically moving it around. A pretty easy way to do that is if you just make like a grid system of holes and then you have a big hole in the middle for your shaft to go through, you can adjust a lot of your C to Cs that way. And so everything can change based off of that. And then you can just measure dimensions and everything should hopefully go together.
do you guys often like have like multiple design drawings and you mix match ideas?
So generally the way that it works is like, for instance, this year you can't really have two intakes. So it's like you have the core superstructure, I keep saying that, but it's like you start with your superstructure and then everything else comes after that. What we do if we aren't sure what idea we're gonna use yet, we often just have like a box on the end of the thing where you're like, this is where whatever intake we decide on is gonna go. And we don't know how that's gonna happen, we don't know how it's gonna work, but we basically say, we're committing to this, because then we have something to work with for mechanical, electrical, and software, and we decide the rest of it as we do more iteration on whatever's the subjective game element.
Go ahead.
For you guys' iteration of your prototypes, you guys start off with like a simpler, just based on a drawing, handmade drawing. After that, after you have one based on handmade drawings, when you're trying to figure out more specifics, do you guys re-prototype with like actual dimensions, or do you guys just use your initial prototypes as like a proof of concept, and then after that, just straight into manufacturing?
So we kind of like to do 2 rounds of prototyping. So the first round is a simple proof of concept, plywood 2x4, and then after that, we take it like not quite polished by any means, but it's like the next step. So that's where you kind of get your grid system of holes, and that's where you get your core dimensions of like, you vary it by like a 1/4 inch or a 1/2 inch each time, and then you can kind of figure out what the more CAD specific stuff, like compression, handoff distance, and stuff like that.
Yeah, like our second round, I think it was like a laser cut wood, so it's a
Yeah.
little bit more refined, but still wood that you can like add holes to and stuff.
Yeah, and if you don't have a laser cutter, which is pretty common, you can basically just like take a grid system of holes on an existing part, just use a center punch in every single one of those, and you have a grid system. And then it does the exact same thing for about 2 minutes worth of work.
You said, I know you said how you like split up your teams, but how many people, like numbers wise?
Hardware design is about 20 people normally. We usually have basically one person who's in charge of each subsystem, and then working underneath them, normally we have 2 to 3 less experienced members who are helping with the smaller stuff like individual tiny parts or part drawings or stuff like that, but they're also working with that veteran member to learn more from them, because we found that the really easy way to teach this kind of thing is in small groups with a person who already knows how to do it, and they just talk to them. If there are no other questions, thank you all for coming. We really appreciate it. And if you have any questions, we'll stick around afterwards.